Now, next property is a division by t. Here, if we multiplied by t, then there is a concept of a differentiation. If division by t, then there is a involvement of a integration. Multiplied by t, then differentiation. Divide by t, then integration, provided the integral will exist. So, if Laplace transform for ft is fs, then Laplace transform for ft divided by t equal what? S to infinite fs ds, provided the integral exists. So, how we find, how we prove this one? Proof of this one is a what? Proof of this one is a what? Here. Now again, to prove this theorem, we use the definition of a Laplace transform. Now, by definition of a Laplace transform, Laplace transform. Here we assume that ft is of a class A function, means there is a existence of a Laplace transform. So, Laplace transform of a ft equal fs equal what? 0 to infinite e to power minus st ft dt. Now, we integrate this expression, means if we write this one is equation number 1. We integrate the equation 1 with respect to s from s to infinite. Integrate first with respect to s from s to infinite. So, what is the left hand side? Left hand side become s to infinite fs ds, and right hand side become s to infinite 0 to infinite e to power minus st ft dt ds. Since s and t be the independent, so we may change the order of integration. So, here first we integrate with respect to s, then we integrate to t. So, here we change the order of integration since they are independent. So, we able to change the order of integration without performing any any modification. So, in the next phase we write this one s to infinite fs ds, and right hand side first we write by changing the order of integration 0 to t, then we write 0 to s, not a 0 to s, means s to infinite. Here we write s to infinite e to power minus st ft ds, then we write a what? Then we write a dt. So, if we integrate the right hand side by parts, then what will happen? With respect to s, what is the integration? This becomes 0 to t, not a by parts. So, 0 to t, not a 0 to t. Basically, here 0 to infinite, by the definition of a, why we write here 0 to t, here 0 to, this one is a 0 to infinite, sorry. So, this one is a 0 to infinite, and if we integrate this function, ft is a free from s. So, we may write this one outside. So, what is the integration? This become e to power minus st into ft divided by what? Divided by minus s. With respect to s, so not s here, it be because t is treated as a constant. So, if t is treated as a constant, so what is the integration, this become minus t dt, limit is a 0 to infinite. Limit is a 0 to infinite. So, this become 0 to infinite, this becomes 0 to infinite if we write a limit. So, this becomes 0 to infinite, 0 to infinite, and this one is s to infinite, sorry, s to infinite, s to infinite. So, here in place of a s, if we write a infinite, then this become what? Limit s tends to infinite, s tends to infinite. Here limit s tends to infinite, or here this become e to power minus infinite. So, what is the value? Here we write not in form of a limit, this become what? 0 minus e to power minus st ft upon minus t into what? Into dt. Into dt. If we put the upper limit, this term become what? First term become 0, means this one, minus, if we put the lower limit, then this become in place of a s, then e to power minus st ft upon minus t. So, if we simplify, then this becomes 0 to infinite, minus become plus, e to power minus st into ft upon t dt. So, by the definition of a Laplace transform of a ft is a e to power minus st ft. So, Laplace transform of a ft upon t, e to power minus st ft upon t. So, this one is a what? Laplace transform of a ft upon t. Laplace transform for ft upon t is a what? 0 to s to infinite fs ds, fs ds. So, if here we write in the next phase, Laplace transform of a ft upon t is a what? S to infinite fs ds. So, what is the application of this property? If we have a Laplace transform for ft, then we are able to find out a Laplace transform for ft upon t. Laplace transform for ft upon t by integrating the fs with respect to s and taking the limit from s to infinite. So, here we are going to solve two numerical problem based on the division by t of ft if we have a Laplace transform of a ft. So, here we are going to solve two numerical problems. First one is a Laplace transform of a sin 2t upon t, and second one is a Laplace transform of a sin squared t upon t. Means here we consider ft is a sin 2t, then divide by t. Here we consider ft is a sin squared t, then divide by the t. So, in order to solve the first problem, let ft equal what? Ft equal sin 2t, ft equals sin 2t. So, if ft equals sin 2t, then by the definition of means by the Laplace transform for elementary function, Laplace transform of a ft equal Laplace transform of a sin 2t equal, as we know that the Laplace transform of a sin at is a upon s square plus a square. Here a is a 2. So, Laplace transform of a sin 2t is a 2 upon s square plus 2 square with a 4, s square plus 4, 2 upon s square plus 2 square. Now Laplace transform of a sin 2t upon t. Now, we use the property of a division by t. So, this one equal what? And here we consider this one is s is a greater than 0, and this one equal to what? This one equal to fs. This one equal s to infinite fs ds. Fs ds. Now, this one is a 2 time s to infinite 2 upon s square plus 4 ds. S square plus 4 ds. So, what is the integration? Now, here s to infinite 2 upon s square plus 4 ds, here we take 2 outside, then 2 into s to infinite 1 upon s square plus 4 ds, and what is the integration of this one? 2 into 1 upon 2 tan inverse s by 2, limit is s to infinite. So, 2 and 2 cancel out. So, what is the result? This becomes tan inverse infinite minus tan inverse s by 2, and this become what? Pi by 2 minus tan inverse s by 2. Tan inverse s by 2. So, this one is answer. Pi by 2. Once we verify the answer, pi by 2 minus tan inverse s by 2. So, this one is answer. So, what is the answer? Laplace transform of a sine 2t upon t is a what? Pi by 2 minus tan inverse s by 2. So, how we solve this one is answer. This one is answer. Now, how we solve the second problem? In a similar manner, we able to find out the solution of a second problem. So, what is the second problem? Second problem is find the Laplace transform of a sine square t upon t. So, here again, similarly as we solve the first problem, here again let ft equal solution, ft equal sine square t, sine square t. So, as we know that, what is the cos 2t? Cos 2x equal what? 1 minus 2 sine square x, 2 sine square x. So, 2 sine square x equal, 2 sine square x equal, this become 1 minus cos 2x, and sine square x equal 1 minus cos 2x by 2, 1 by 2. So, this one is a, here we use this result. So, ft become what? Now, ft become sine square t equal 1 by 2 minus cos 2t upon 2. Now, using the formula of Laplace transform of a elementary function, or formula of a Laplace transform of a elementary function, Laplace transform of a ft, ft equal Laplace transform of a 1 by 2 using the linearity property, 1 by 2 Laplace transform of a cos 2t, cos 2t. Now, we know that this become 1 by 2 into Laplace transform for 1 is a 1 by s minus 1 upon twice the Laplace transform for cos 2t is a s upon s square plus 4, s square plus 4. So, this one is a Laplace transform of a ft, Laplace transform for ft. This become 1 upon 2s, 1 upon 2s minus 1 upon 2 s upon s square plus 4, s square plus 4. Now, using what? Now by property of a division by t, Laplace transform of a ft by t, ft by t equal s to infinite fs ds, fs ds, and here we assume that this one is a what? This one equal fs, this one equal fs. So, here we write fs, Fs equal, this become s to infinite. Fs is a 1 upon twice s, sorry, not here, 1 upon 2s minus 1 upon 2 s upon s square plus 4, s square plus 4. So, here this one is a ds, this one is a ds. Okay. So, this one is a ds. So, if we integrate with respect to s, what is the integration of a first term? This become 1 upon 2 and log s, and what is the limit? Limit is a 0 to infinite, 0 to infinite, 0 to infinite, and second one is a minus 1 by 2 into 1 by 2 log of a s square plus 4, log of a s square plus 4, log of a s square plus 4. This one is a, and taking the limit from what, 0 to, not a 0 to infinite here, this one is a s to infinite, s to infinite, s to infinite. So, or we may write this one is a 1 upon 4 outside, this become 2 time of a log s minus log s square plus 4, limit is about 0 to s to infinite, limit is s to infinite, and this may be written as 1 upon 4, this become log s square, and this become in a denominator, this can be written as log of s square upon s square plus 4. What is the limit? Limit s to infinite, limit s to infinite, limit s to infinite. Now, we simplify this one. So, Laplace transform of a ft upon t, or Laplace transform of a sin square t upon t become what? 1 upon 4 log of a s square upon s square plus 4, limit is s to infinite. So, if we put the limit infinite, so this become what? 1 upon 4 limit s tends to infinite log of a s square upon s square plus 4 minus 1 upon 4 log s square upon s square plus 4. So, if we take the limit here, s square become outside. So, this become 1 upon 4 limit s tends to infinite here. If we take s square outside here, s square, and here s square outside, then 1 plus 4 upon s square cancel out, as s tends to infinite, this become log 1 minus 1 upon 4 log s square upon s square plus 4. So, what is the answer? This becomes 0, 0 minus 1 upon 4 log of s square upon s square plus 4, or log of s square plus 4 upon s square, using the property of a log. Log s square plus 4, sorry, 1 upon 4 outside, 1 upon 4 outside. So, this one is the answer. 0 minus 1 upon 4, 1 upon 4 means a minus 1 become here minus 1. So, you may write one step more, means here 1 upon 4 log of s square upon s square plus 4 to power minus 1. This can be written as 1 upon 4 log of s square plus 4 upon s square plus 4 upon s squares. This one is the answer. Once we verify the answer, this one is the answer. So this one is all about this lecture. So what is the summary of this lecture? First we discuss about a class A function. Class A function, if ft is from the class A function, ft is a class A function, then there is a certainty of existence of a Laplace transform. And what is a class A function? A function is said to be a class A function if a function have exponential order and function is either continuous or piecewise continuous from t is equal 0 to infinite. And what is the exponential order? Exponential order, a function have exponential order if limit t tends to infinite, ft into e to power minus alpha t tends to 0. And then we discuss about a change of a scale property and how we means a multiplicative property multiplied by integral power of a t in a function ft and divide by the t in a function ft. Then how we find the Laplace transform, means if we have a Laplace transform for ft, then how we find the Laplace transform for f of at, Laplace transform of t into ft, t square into ft, t cube into ft and up to t to power n into ft. And if we have a Laplace transform for ft, then how we find the Laplace transform for ft upon t. So I hope all of you enjoyed this series of a lecture of a Laplace transform. Thank you joining my video lecture. Thank you very much.